In part 2 of this two-part video series, we'll explore non-parametric classification trees. Also known as decision trees, these are common tools both within and beyond technical settings. For example, by starting at the top and following a sequence of yes/no questions, the tree here can help you decide whether or not to use an emoji in a text message. In machine learning, we can use a similar approach to predict the outcome of some y variable by answering a series of yes/no questions about our predictors x. The resulting classification tree is like a real tree, but upside down. Its roots, or the root node, starts with all data points. And through a series of yes/no questions, it filters the data points into the leaf nodes, or terminal nodes. These nodes end in a classification of y. To consider how this works, consider building a classification tree of land use using only the vegetation index, NDVI. Our root node starts with all 277 images in our sample. The next step is to make a binary split, or split these images into two groups that are as distinct as possible. To this end, notice that at a vegetation index of roughly -0.01, the asphalt images are almost perfectly distinguished from the grass and trees. Thus, we have our first split in the tree. Conventionally, if a split condition holds, then we go left, otherwise we go right. In this case, if an image has a vegetation index below -0.01, we'll predict that it's asphalt. Above -0.01, it gets a bit murkier. But since among the images that fall above -0.01, 111 are grass and only 105 are trees, we'd predict grass. Now, if we stopped our tree building here, we'd do a great job of classifying asphalt, but a terrible job at distinguishing between grass and trees. So let's keep splitting. Among images with NDVI above -0.01, the next best binary split is at a vegetation index of 0.25. Specifically, when NDVI is below 0.25, we'll classify an image as grass. Otherwise, we'll classify it as tree. We could keep growing our tree and making more splits, but it looks pretty good at this point, so let's stop here. We can now use this tree to classify a new image. For example, consider a new image that has a vegetation index of 0.2, represented by the red dashed line. Since 0.2 is not below -0.01, we go right in the first split. And since it is below 0.25, we go left in the second split. Thus, we predict that this image is of grass. Next, consider how to build a tree using two predictors. In any given split, we can only use information from one predictor at a time. It turns out that a vegetation index of -0.01 again best separates our images into two groups. Below -0.01, the images are almost exclusively asphalt. However, above -0.01, we can continue to better distinguish between grass and trees. Within this group, the best binary split again occurs at a vegetation index of 0.25. Below 0.25, the images are almost exclusively grass. Above 0.25, there are more tree images than grass images, but let's make one more split to better distinguish between the two groups. Among images in this group with vegetation indices above 0.25, the best binary split is at a greenness measure of 211. Above 211, most images are grass, and below 211, most are trees. Let's now use this tree to classify a new image, represented by the black X, that has a vegetation index of 0.4 and a greenness of 225. Since a vegetation index of 0.4 is not below -0.01, we go right in the first split. And since it's not below 0.25, we go right again. Finally, since the greenness measure is above 211, we go left. Thus predict that the image is of grass. When plotting trees in R, it turns out that the information about each node goes beyond the split conditions. Consider the root node. 100% of images start in the root node. The numbers above this indicate the category breakdown within the node. Mainly among the images in the root node, hence images in our sample data, 21% are asphalt, 40% are grass, and 38% are trees. There's some rounding happening in the background here, otherwise these would add up to 100. Finally, since the highest proportion of images in this particular node are grass, the predicted category corresponding to this node is grass. Similarly, let's interpret the rightmost leaf node. 30% of images fall in this node, and any image that falls in this node is classified as a tree. Among these, 0% are actually asphalt, 12% are actually grass, thus are misclassified in this node, and 88% are trees, thus are correctly classified in this node. Stepping back, here's what we've learned about the classification tree algorithm. Using what's called recursive binary splitting, we start at the top of the tree with all of the data points, we create the best binary split between the data points, and then we repeat step 2. That is, we continue making splits until we're done. Though this is the general idea, we've definitely ignored some important details. First, how do we create the best split? How is the best split determined or identified? Second, until when do we continue to make binary splits? How do we know when to stop splitting? Let's consider this question first. The process by which we identify when to stop building our tree is referred to as pruning. With real trees, pruning or trimming branches can be important to tree health. Similarly, it's important to prune or cut back branches of a classification tree. But of course, this is going to be a Goldilocks problem. If we prune too many branches, our tree is going to be overly simple. But if we prune too few branches, for example, if we let our tree grow and grow and grow until each individual data point has its own leaf node, our tree is going to be overfit to the sample data. So it turns out that there are multiple tuning parameters to consider here, each of which we have to pick. One parameter is the maximum depth of our tree. That is the maximum number of splits to make from the root node to the leaf nodes. For example, for the tree here, suppose we want to have a maximum depth of 2 splits. In that case, we'd prune all branches that occur after the second split. Another tuning parameter to consider is the minimum sample size in each node. For example, suppose we started with 150 data points, and the first split divided these into 2 groups of size 100 and size 50. Our next split then divided the group of 50 into 2 groups of size 30 and size 20. We continue splitting from there, but again, if we split too many times, we end up with small leaf nodes that are overfit to our sample data. With that, suppose we want at least 40 data points in each node. In this case, we'd stop after the first split. Beyond that, our nodes get smaller and smaller, basically smaller than 40. Yet another consideration when pruning trees is the cost complexity parameter. This is typically represented by the Greek letter alpha. To understand cost complexity, it's important to first note that each new split is either going to maintain or improve classification accuracy, whether by a little or a lot. But these additional splits also come at the cost of making the tree more complicated. With that, the alpha cost complexity parameter, which can take any non-negative value, penalizes the number of splits in a tree. At the extreme, when we set alpha to 0, there's 0 penalty. That is, we can make a split even if it doesn't improve our classification accuracy. However, the more we crank alpha up, the greater the penalty we place on making new splits. Mainly when alpha is really big, we can only make a new split if it improves the classification accuracy by a lot. Going back to the classification algorithm, we now have a sense of when to stop making binary splits. But we still haven't addressed how these splits are made. Let's do that. Perhaps not surprisingly, we don't just guesstimate the best split from a plot. We use a mathematical metric. Here, the Gini index of a node measures the probability that randomly classifying a randomly selected data point from the node leads to a misclassification. A formula for the Gini index is provided here for the general case in which our Y categorical outcome has k different categories, with P1, P2 up to Pk being the proportion of node data points that fall into each category. Breaking this down, the first term in the sum represents the probability that, from this node, we randomly select a point from category 1 and then misclassify it as something other than category 1. We go through this calculation for every category, ending with the probability that from this node, we randomly select a point from category K and then misclassify it as something other than category K. In total then, the sum calculates the overall probability that randomly classifying a randomly selected data point from the node is going to lead to a misclassification. Let's consider some examples. Suppose we want to make a binary split for a sample in which there are 3 red objects and 3 blue objects. The split here would be perfect. It perfectly separates red from blue. Let's examine how the Gini index will represent this perfection. First, consider the first node. Here, as represented by PR and PB, 100% of the data points are red and 0% are blue. Plugging these into the Gini index formula, we get an outcome of 0. You can focus more on the outcome than on the calculation here. Mainly, the Gini index of 0 indicates that if we randomly classify a randomly selected data point from this node, there's a 0% chance that it'll be misclassified. All of the data points are red, and so any randomly selected data point is also going to be classified as red and therefore correct. Similarly, since all data points in the second node are blue, it too has a Gini index of 0. Of course, nodes aren't always perfect. In the split shown here, though the first node is still only red, with a Gini index of 0, the second node has a mix of categories. 2 of 5, or 40%, are red, and 3 of 5, or 60%, are blue. The resulting Gini index is 0.48. That is, if we randomly classify a randomly selected data point from this node, there's a 48% chance that we'll misclassify it. Stepping back, as a probability, the Gini index is a number between 0 and 1. The smaller the index, the more homogeneous or pure the node. At the extreme, when a node is perfectly homogeneous, that is, all data points in the node are in the same category, G equals 0. Finally, the quality of the individual nodes in a split can be combined to evaluate the overall quality of a split that created the nodes. Specifically, the overall quality of a binary split is the weighted average Gini index of its nodes. The weights here are determined by the proportion of data points that fall into a node. Basically, the more data points that fall into a node, the more weight that node is going to have in measuring the quality of the split. In our first binary split option on the left, both nodes had a Gini index of 0. Thus, their average Gini index is also 0. In our second binary split option, the weighted average Gini index is 0.4. This result put only 1/6 weight on the 0 index of the first node and 5/6 weight on the 0.48 index of the second node. That is, it gave more and proportional weight to the larger node. Now, if we had to pick between the 2 possible splits here, we'd pick the first one. In general, when building splits, the tree algorithm seeks to minimize the average Gini index of the nodes. Thus, it seeks to minimize the classification errors. These observations fill in the final details of our tree algorithm. Using a recursive binary splitting algorithm, we start at the top of the tree with all of the data. We then create the binary split, which minimizes the weighted average Gini index, thus maximizes node homogeneity. We then continue making splits until we meet some stopping criterion, which is controlled by parameters such as maximum depth, minimum sample size in each node, and cost complexity. In conclusion, trees are great. In comparison to the k-nearest neighbors algorithm, the tree visual provides more insight into the relationship between y and x. And trees are eager, not lazy learners. Mainly, we only have to build one tree, and then we can use this to classify every new data point. But like any algorithm, trees of course have some drawbacks. Like backward stepwise selection, trees are greedy. At each step in the algorithm, we make the best split possible in that moment. But the split cannot be undone, and it does not consider what split might be optimal in combination with future splits. For example, the best first split in a 1-split tree might not end up being the best first split in a 5-split tree, but it's the split that we're stuck with.